honored that everyone is freshly caffeinated. That's awesome. I'm Taylor Higgins. I am a brand new assistant professor at Florida State University. But today I'm actually going to talk about my final PhD work with my colleagues at the University of Notre Dame. So today I'm talking about data-efficient human walking speed intent identification for lower limb assistive robots. So traditionally and somewhat more often, we see intent recognition being done through signals that are directly attached to the human. So by these signals, I'm referring to electroencephalography and electromyography. So like I said, these signals are great because they do directly attach to the human and relate to volitional signals from the human. But unfortunately, they can be very cumbersome to prepare and put on. And this is especially unfortunate in settings where we use assistive robots, like in physical therapy settings, where speed in donning and doffing the device is very important. Unfortunately, once we get these sensors all on, they often also succumb to noisy and inconsistent performance as the individual moves and perspires. Ideally, and we have challenged ourselves here to rely only on sensors that are already on board the assistive device. So, for example, we might consider signals like the commanded motor currents and the motor encoder joint angles that are measured at each of the power degrees of freedom of most assistive robotic devices. Here I'm showing the ExoGT. So unfortunately, these sensors do not directly sense the human. They sense the human through interactions with the robot, so indirectly. But fortunately, there's no extra sensor placement needed, making donning and doffing the device fairly simple. And because they are rigidly attached to the device, we often see more consistent performance. So we decided to develop an intent recognition algorithm based on these onboard sensor signals that takes into account the fact that walking data has uncertainty. So what I'm referring to here, for example, showing the knee angle with respect to time across several gait cycles. If we zoom in at a single time step, for a single gait cycle, we might be at one angle, another we might be at a slightly different angle, and so on. What we can do is characterize that uncertainty by finding a mean and a standard deviation of where we expect to be at that time step. And we can do this for all time steps of the gait cycle to fully characterize the uncertainty across the gait cycle. And we might even go so far as to say that we expect there to be a Gaussian distribution that's characterized by this mean and the standard deviation at each time step of the gait cycle. Now here I'm showing only univariate data, so the only signal here is the knee angle, but this idea extends fairly simply to multivariate signals, simply by moving from a univariate Gaussian distribution to a multivariate Gaussian distribution. So here we're characterizing the gait cycle as having a mean vector and a covariance matrix at each time step of the gait cycle. And we can build this model of the gait that's characterized by its uncertainty based on a set of training data where an individual is walking with constant gait speed and tension, so where they're walking at the same speed for a set length of time. Now by assuming these Gaussian distributions, we're afforded a new metric, a new distance metric that is useful to us. This distance metric is called the Mahalanobis distance. And essentially it scales the Euclidean distance between a new incoming data point and the mean vector of this Gaussian distribution by the uncertainty in each degree of freedom, so that inverse covariance matrix in the middle. So we might think about this in terms of a single degree of freedom. What this says is that if your single degree of freedom signal has lots of variance, it's a very broad Gaussian distribution, our new data point needs to be extra far away from the mean for us to consider that new point different enough from that Gaussian distribution to be considered as an intent change. So this idea we extended into a full algorithm for detecting online intent recognition. So we take one new data point, so one new sample from all of our sensors that we have available. We compare it to the appropriate Gaussian distribution that we have from our model, and we take the Mahalanobis distance. So the Mahalanobis distance also lets us get at this idea of whether this new data point belongs to that constant intent model or not. So if that Mahalanobis distance is above some threshold, we say it's indicative of an intent change, and if it's below some threshold, we say that there is no intent change. We've also considered whether the user is making a speed up or a slow down intent change by comparing the most recently completed gait cycle to the speed of the gait cycles that were used to build the model in the first place. We tested this algorithm with 15 able-bodied subjects who walked on a treadmill and performed, or first they gave us 5 minutes of constant speed intent data, so they walked at 1.4 meters per second for 5 minutes. Then we trained our model, and then we tested our model as the user made small, medium, and large speed up and slow down intent changes. Just very high-level results for our quick 6 minutes. We were able to achieve up to 87% accuracy. Which we were very happy about, considering we only had 5 minutes of constant speed intent data to train our model. We saw the best accuracy for our largest intent changes, which is fairly intuitive. We were also a little bit better at identifying speed up changes as opposed to slow down changes. If you would like to see more details about this idea, please see our up and coming wearable technologies paper, but I would of course be very happy to take questions and talk to you offline. Thank you very much. Yes?
How do you distinguish speed up intention from not wanting to fall on your face intention?
That's a great question. We didn't. So the assumption here is that the human is stable at this point. What I think you might be getting at is the possible danger of saying that the user wants to speed up when actually they need to stop because they're unstable. So the great thing is, at no point am I actually implementing this intention change. It is simply a signal that I can use later on to determine what is the most appropriate robotic action, which may have other signals involved to determine whether the speed up is actually appropriate or not. So you might look at the stability of the robotic device at that time and say, even though the user would like to speed up, or it looks like they would like to speed up, that's not the right idea right now. Great question, thank you. Yes?
How do you know what phase you're in? Do you do anything, like if someone were to have some kind of discontinuous phase thing, like they do a stutter step or something, and now all of a sudden there's some phase offset, like are you just kind of marching forward in time on this thing? Or?
That's a great question. We are essentially marching forward in time, but we broke up the gait cycle into discrete phase sections. So for instance, double support starts at heel strike, and I march forward in time until I start the next phase where I lift off my back leg. And then I restart, and I start over at time step 0. So that resetting gives me a little bit smaller discreteness, I guess. In the back?
Yeah, would you expect the results to be different if you will normalize the time for each step so that it would be always the same? So the phase, the same gait cycle phase would be the same in all steps.
Right, we did try normalizing the gait cycle from 0 to 100%, but actually the normalization throws out data that's very useful for determining the intention. So if you are running long in time, that is actually somewhat baked into some of the details of this algorithm, and we found that key idea to be important. So we did not normalize by time. Right here.
How do you plan to generalize this idea if you have to make multiple decisions?
This is a great point. So currently the algorithm, the way that I've described it, only differentiates between speeding up and slowing down from your baseline, which was 1.4 meters per second. Since this experiment was run, we've actually taken some more data where we had individuals walk at a range of different speeds, each for about 5 minutes of time. And if you think intuitively, the Mahalanobis distance should get larger the larger the speed change you intend. And this is actually holding true. So if you have various degrees of speed change from baseline, your average Mahalanobis distance gets bigger the further away from baseline you are. So even if you give only one baseline, I can tell by the magnitude of the Mahalanobis distance basically how far away you're wanting to change. And in that way you can change multiple times. So if your Mahalanobis distance grows in amplitude, you can then bump up another speed. Does that answer your question?
I guess it answered the question, but my thinking was more along the line of if you have different tasks that you want to generalize this to.
Different
how
tasks.
would you go about it?
That's a great question. So right now I've really only looked at gait and gait speed. Yeah, I think you would end up needing to train different models for different tasks because it would it doesn't lend itself well to changing from walking to a different task. Okay, great.
One more question while I'm thinking.
So what do you see the application of this? Is this more for like rehabilitation wearable robotics or like someone cooking in like a factory type thing? And if it's for rehab, how would your model deal with like the inherent like increased variability for someone with like a stroke subject or something like that?
I do think right now it's most suited for rehab. The idea being that the more control that you have over the nature of your gait, the more kind of involved you are, the more, wow. The more devoted you are to your rehab. I would love to see it out in the world, but I think we need to be able to recognize other intentions besides gait speed in order to be out in the real world. I do think that the fact that we can build this model and achieve fairly good accuracy with only 5 minutes of training data means that even the stroke patient who comes in can come in and give their 5 minutes, which captures their standard deviation. That will be taken into account. Great, great questions, thank you.